All right, here we are on the last ones that use proportions. And there's a bunch of other types of problems too, but we're kind of focusing on these ones because they appear a lot. But it's used proportions, which means it's either a cone or that like shadow problem. Number 10, a lot of the information is given to us already. We know it's a cone. We know the volume of the cone. We know dRdt, right? They give us dRdt is 2, and they give us this relationship h equals 3r, which is that finding that relationship is what most students struggle with when doing the cone problem. And in this problem, it's just given to you, right? So that's kind of nice. We want to know, find the rate of change of the volume, right? So the thing that we want is dV dt, right? So let's write that. I want dV dt. And I have this volume equation, right? We have this volume. And it's really tempting just to right away, like, take the derivative of the volume equation. And, like, you know, that is okay. But if you get to this problem and you just do that, like, there's an r squared and there's an h on the right-hand side. That's two different variables being multiplied. You would have to use product rule on this, which complicates things, right? And this is the reason that in this one, they give you this h equals 3r. And this is the reason that this is a proportion problem, is because in every time you see this cone, you're most likely going to have to use this relationship that h equals 3r, right? So in this case, because I'm given dr dt, if I can write my volume equation in terms of r, then I won't have to worry about h, right? So they tell me h is 3r. So the first thing we actually want to do is, because I know that relationship, we're kind of doing like a substitution, like solving system equation substitution, right? We're going to actually replace my h with 3r and then simplify. And sorry, that's we can do better than that. If I multiply 3r times 1/3, I'm just going to get 1, right? So it's going to be volume equals pi r and then pi r cubed, because r times r is r cubed, right? So now I'm left with this much simpler equation that I can take the derivative of, right? We're going to take the derivative of that, and we're going to get dV dt, the derivative of volume with respect to time, is 3 pi r squared times dr dt. Right, and then let's just go up here and we'll plug in some values. I want dV dt, so that is not going to be plugged in anything. 3 pi is a constant. We're going to put r there, and then we're going to square it. We're going to put dr dt there. Right, so they tell us dr dt is 2, so that's here. And for part A, it says r is 6, so I put 6 there. Right, and then I just work that out, and we're going to get dV dt equals, 6 squared is 72, 72 times 2 times 3 times pi. So basically, it's going to be 432 pi. Or what? What is radius measured, or volume? What is volume measured in? It's going to be inches cubed per minute, because our time is minutes, right? So that's A. Part B is the same problem, just at a different time value, right? Or a different r value. So that dr dt is still 2. The only difference is the radius is now 24. So now we're going to do 24 squared times 2 times 3, which is going to give us 3,456 pi inches cubed per minute, right? So there's our answers for that one. And it's, you can see, like, it's not that bad if you're given the equation and you're given that secondary equation. It's just taking the derivative and plugging numbers in. That's not that bad. It's when you get to like 11 and beyond that makes it much harder, right? So here we go. Water is being poured into an inverted cone. Just means it's upside down, right? You have this upside down cone. It's being poured in at a rate of 3 cubic centimeters per second. That's a volume, right? Cubic centimeters is a volume, so dV dt is 3. That's given to us. The cone has a maximum radius of 8. I'm going to call that maximum radius big R, right? And it has a maximum height of 32. I'm going to call that maximum height 32. And I'm going to call it big H, right? At what rate is the height increasing when the height is 6 centimeters? So it's saying like we're filling this thing up with water, right? And so there's this other little height of the actual height of the water, not the height of the actual cone, but the height of the water inside that bigger cone. So we're going to call the height of the water inside the bigger cone little h, and it also forms a little r going across, a little radius going across. So if you see this triangle I have over here, I have a big R, a big H, a little r, and a little h. The little r and the little h represent the actual height of the water. And we want to find dH dt, and we're given this volume. So our primary equation is going to be the volume equation, right? Volume equals 1/3 pi r squared h. But we need this secondary equation because, again, this volume equation has an r squared and an h, and then you get these product rule and you don't have enough information. So we need this secondary equation, which is the using similar triangles and the proportions. If I take big H and divide it by big R, then I will get little h over little r, right? The corresponding sides, the ratio of the corresponding sides are equal. Geometry, right? So here's my secondary equation. I know H, I know big H, I know big R, right? They gave me that. They said big H was 32, and big R, the maximum size of the cone, was 8. And little h and little r are changing, right? Think about it. Big R is not changing. Big H is not changing. Those things are constant. Those are the size of the cone, right? My cone is not changing. The level of water inside is changing, but which is the height of the water, and the R is changing, right? So this basically becomes 4 equals h over r, or we can, to simplify it, we would get 4r equals h. Now, because I want dH dt, that means I want my volume equation in terms of h. I only want h's there. Unlike the other problem where I wanted dr dt and I had r's only, in this problem I want dH dt, so I need to simplify my volume equation so it only has h's, right? So we're going to write volume equals 1/3 pi. If it's only going to have h's, that means I need to replace the r with this secondary equation, right? So I'm going to replace this r with h is 4r, right? Which means that r is h over 4, right? If I solve that. So I'm going to replace this with h over 4. And that's going to give me all h's, right? And then we're going to simplify. We're going to get volume equals, if I square this, I'm going to get a 16 on the bottom. So it's going to be 3 times 16 on the bottom. 1 over 48. There's a pi on top. So 1 times pi. H squared times h is going to be h to the 3rd. So now I have this equation that it has that weird fraction in the front, but at least it doesn't have 2 variables. I don't need to use product rule on it. Okay, so let's go over way on the right hand side and let's take the derivative with respect to t of our new volume equation, and we're going to get dv dt equals pi over 48 is just a constant, so pi over 48 times 3h squared dH dt. And then we can plug in the things we know. We know dv dt is 3. This is just a constant, 3 pi over 48, which actually we can simplify it. 3 pi over 48 is the same as pi over 16 times h squared. Do we know what h is? When the h is 6, right? So h squared times dH dt, but remember dH dt is a thing that we want. So that's the thing that's not going to be replaced. And so I'm left with this. And if you do this, like you can imagine, I could just divide both sides by this, right? If I want to do that first. So it'd be like 3 over 36 pi over 16. And then, instead of dividing, you multiply by the reciprocal. So it'd be 48 pi over 36, right? 48 over 36 pi. The 48 coming from 3 times 16. And then I can simplify this a little bit. 48 divided by 36, they both are divisible by 6, right? If I divide them both by 6, I would get 8 over 6, which simplifies even more to 4/3, and there's a pi on the bottom. So 4 over 3 pi, this is dH dt, where h is measured in centimeters, and time in this is measured in seconds. So we get 4 over 3 pi centimeters per second. We'll right. Let's move on. Shadow problems are really confusing at first to try to figure out how to set them up and how to think about them, but once you get the hang of it, they're all the same. So here's the drawing, right? I have Michaela, who is this little stick person in the middle. She's 7 feet tall. And I have a lamppost that's 21 feet tall over here, shining light in every direction. And when you shine a light, if that's the only source of light, then you have a shadow, right? So as this light comes down, there's a shadow created by the light that her body blocks, right? And we're going to call her shadow C. I would use S, but it looks like a 5 and it gets confusing, so I'm using a C. And then X is the distance between Michaela and the lamppost. All right, and right now she's 5 feet from the base of the lamppost. So they give us that dx dt equals -3. That's because she's walking towards the post. Every second she gets 3 units closer. That x distance gets smaller. And they want to know dc dt. They want to know the rate of change of the shadow, where c is a shadow, with respect to time. And so the way this works is there are 2 triangles in there, right? There's a big triangle and a little triangle, and they are similar triangles. So we can write a proportion, right? We can write the big height divided by the big side length, right? The big height is h, and the big side length is the x plus the c, right? To get that whole side, you need to add x and c. So over here I have big H divided by x plus c. That ratio will be equal to the ratio of the little height, which is little h, to the little side length, the little base, which is just c. And so that gives me an equation. And some of these things are constant, right? Like big H is constant. The height of the lamppost is not changing. It's not a tree. It's not going to grow bigger. And then little h is also constant. The height of Michaela, she's not going to grow at all right now, right? So that's also constant. So we can go and like plug numbers in there. We're going to get 21 over x plus c equals 7 over c. And then just like rework this equation so like, you know, it's nicer. Multiply, cross multiply, we're going to get 21c equals 7x plus c, and you can distribute, and you get 21c equals 7x plus 7c. You can move that 7c over to get 14c equals 7x. Divide both sides by 7, and you will get 2c equals x. Right, and so that becomes our primary equation. Basically, x equals 2c. And we want to know dc dt. So we're going to take the derivative of this, and we're going to get dx dt equals 2 dc dt. And then we just plug in our number for dx dt. dx dt is -3. And you can see that we just divide both sides by 2 to get dc dt equals -3 over 2, where the length in this is measured in feet and the time is measured in second. So we get that. All right, as you can see, hopefully that it's like the setting up part that's confusing. Number 13 is very similar. It's a shadow problem. The heights of the people are different, but it's the same basic problem. So you can see I set it up the same way. And then there's a difference here in the last question. It says how fast is the tip of the shadow moving? The tip of the shadow moves at the same rate as the distance between the person and the pole plus the rate of change of the shadow. So here's our equation. Again, we did big height over big base, which was 40 over x plus c, and that's equal to little height over little base, which is 6 over c. And then we're just going to go ahead and solve this thing. We're going to get 40, or we're going to simplify. 40c equals 6x plus 6c. Right, I went in and distributed as well. Move the c over, we're going to get 36c equals 6x. Divide both sides by 6, we're going to get x equals 6c. We want to know dc dt, so we take the derivative of both sides. Right, take the derivative, and we're going to get 6 dc dt equals dx dt. We know dx dt is given to us at 6, so we put in a 6 over there. We divide both sides by 6. We divide both sides by 6, and we get dx dt. Oh, sorry. Let's go ahead and plug these in, right? So we have 6 dc dt equals 6. No, he moves at a rate of 5. I don't know why I wrote that. Sorry. dxct is not 6. dxct is 5, right? It's right up here, moving at 5 feet per second. So dxct is 5, so it's going to be 5 over 6 feet per second. That's the rate of change at which the shadow changes. That's the answer to part A. And then the answer to part B is simply just adding dx dt plus dc dt. So it's basically 5 plus 5/6, which 5 is 36 plus 5/6 is going to be 35/6 feet per second. And that's how fast the tip of her shadow is moving. Because it's the tip of the shadow moves, you know, I have to combine the rate at which she's moving with the rate at which the shadow is moving. So it's moving faster because there's two things moving. All right, continue. Another cone problem, which is solved in much the same way. These last two are, so I think let's go to move on to the other ones, right? I think like with the things we did before, you should be able to follow that same process and find this one, right? So like in this one, even like you don't have to use the proportional triangles, like it just gives you the radius is 8 times the height, right? So that's nice. And then the next one, it doesn't give it to you, but I have it here for you, right? There's that, and you can finish it from there. Okay, I want to go to these ones because they're a little bit more involved, and it's nothing terribly different, but it's the same. So here we're given dv dt is 20, right? They tell us that here it's being added at 20. We want to know all this stuff when the height is 6, right? And they tell us, which is really important, they tell us that the base diameter is always twice the height. The thing about being given a diameter is like, oh, thanks, but like nobody cares about diameter in math, right? They always care about the radius. So what I did down here is go and convert the diameter to a radius, right? If the diameter is 2 times the height, then the radius is simply equal to the height, because you know the radius is half the diameter, so half of 2h is h. All right, so we know that r is always equal to h, which is really cool. And this is actually like a real life thing too, so that's kind of nice. How fast is the radius of the pile changing? So that's dr dt when h equals 6. We're going to use our volume equation, right? We know that volume equals 1/3 pi r squared times h. Because I want dr dt, I only want r's in my equation. So before I do any calculus, I'm going to go ahead and replace my h with an r, which is going to give me pi r cubed, right? Because I know h equals r, right? So I can do that. And then we can take our derivative with respect to time. How is it changing with respect to time? And we'll get dv dt equals 3 times 1/3 is just 1, so pi r squared dr dt. And we plug in the things we know. We want dr dt. We know dv dt, right? dv dt is 20. We know r. Ooh, we don't know r yet, so we're going to have to find r. And dr dt is the thing we want, so that's the thing we can't plug in for, right? We don't know r, but we know h, right? We want to know when h equals 6. And I also know that r equals h. So if h equals 6, then r equals 6 as well, right? So that's going to be 36 pi. We're going to divide both sides. We're going to get 20 over 36 pi equals dr dt. Do some simplification and divide top and bottom by 4 to get 5 over 9 pi. So it's going to be 5 over 9 pi. This is a radius. This is going to be measured in inches. And then the time is seconds in this case. So that's number 1, part A. Part B is how fast is the diameter of the pile changing, right? So I know the diameter, so here's over part B. We want dd dt, right, where that big D is the diameter. I know that the diameter is 2 times the radius. And if I want dd dt, then I can just take the derivative of this. dd dt is going to equal 2 times dr dt. And I know dr dt, right? dr dt is 5 over 9 pi. So dd dt is going to equal 2 times 5 over 9 pi. And that gives us 10 over 9 pi, right? So the radius, the diameter is just simply changing at twice as fast as the radius because it's always twice as big as the radius, so it must just maintain that relationship, right? For the next one, we want dh dt, where r, we know r is equal to h. So like if r is always equal to h and r is changing at 5 over 9 pi inches per second, what must h change at, right? You can kind of just like logically go through this, right? If they're equal and they're always equal and one is changing at a certain rate, then the other one must change at that exact same rate, right? So we can kind of show that here as we know r is equal to h. So if I take the derivative with respect to time, we're just going to get a dr dt is equal to dh dt, right? The rate of change of r with respect to time is equal to the rate of change of h with respect to time. And I know dr dt, right? I figured that out over here. So this is 5 over 9 pi inches per second equals dh dt, right? Just plugging it in there. Same answer. And then the last one is tricky, but not that bad. It says the angle of repose is defined to be the steepest angle at which dry, unconsolidated sediment is stable. So each type of sediment would have a different angle of repose, right? Like sand would have a different one than clay. And obviously clay would be really high because you can stack it up, but then that would have a different than salt, which would have different than sugar, which would be different than just like some dry dirt. But the angle of repose is basically the angle that it forms with the ground as it gets stacked up, right? We want to know what is the sand pile's angle of repose and how fast is it changing. So basically we need to figure out what is the angle of repose, right? So we have this angle theta up there. Let me draw it down here. We have this angle theta. We know that this is the height and this is the radius, right? And so what relationship can we create between the opposite side to the angle and the adjacent side? Well, it's tangent, right? So tangent theta is going to be r over h. And we know that if r equals h, right, we know that r equals h. So I can kind of replace h with like r and simplify this. So its tangent is going to be r over r, which means that tan theta in this case has to equal 1, right? R divided by r is 1. So then you have to think to yourself, well, tangent of what gives me 1? Right? Tangent of what gives me 1? Please, radians, please, not, does it say degrees over here? Doesn't say degrees, but we can do both. Tangent of what gives me 1? Well, tangent is sine over cosine. So if it's going to give me 1, then it has to be the same x coordinate as the y coordinate. And the only time that happens is at pi over 4, or 3 pi over 4, or 5 pi over 4. But we're only concerned about the first one, right? Because this is like first quadrant. So the answer is theta equals pi over 4, or if you prefer, that's 45 degrees, right? How is the angle of repose changing? Well, that would be take the derivative, right? If I want the angle of repose how it's changing, it's d theta dt. I would take the derivative of my equation, which is my equation is tan theta equals 1, right? Take the derivative and get secant theta times d theta dt equals 0. You divide both sides by secant and you get d theta dt equals 0 divided by secant theta, but 0 divided by anything is 0, right? So d theta dt is 0. It's not changing, right? By definition of what it is it's the angle at which it will build itself up always, right? So it doesn't matter how high it is, that will be the angle always, which is kind of cool. All right, so last one. A snow cone is leaking, right? So imagine like you have a certain amount of snow cone in there. It's leaving the cone, right? Which means the volume is diminishing, right? The amount of snow cone you have is leaving. So they gave you dV dt is negative 2 inches cubed per minute. And they give us like the top radius is 2 and the height is 5 of the cone itself. All this stuff should be figured out when the depth is 3, right? So for part A, it's asking how fast is the radius of the raspa changing? So they want dr dt. Okay, so let's start this. The volume equation we're going to use is 1/3 pi r squared h. I want dr dt, so I want to try to figure out how can I rewrite this equation with only r's and the v. The v is fine, but only r's on the right hand side. So I need to come up with this secondary equation, which is with these triangles, right? I have this big R, they told me is 2, and the big height is 5. They told me this, right? And then I have a certain amount of RASPA in there, whatever RASPA is, I don't know, but and it says, you know, that's a little r and a little h. So we can create this other relationship, this other secondary equation, which is going to be big H over big R equals little h over little r. And big H and big R don't change, so that's why I went ahead and plugged those numbers in, right? Those are not changing. Those are the size of the cone, right? You don't buy a cone and the cone's like getting bigger and smaller. It's the stuff inside that's bigger or smaller. So basically we have 5r equals 2h. And because I want dr dt, that means I need to replace h with something. So I want to solve for h. I want 5r over 2. And this is what's going to replace my h up here, because I want it only in terms of r, so I can find dr dt. And we will get volume equals, this is going to be 10 pi, what am I talking about, 10 pi? It's going to be 5 pi over 6 times r cubed, and then we can take the derivative because we want dr dt, and we'll get dv dt equals 15 pi over 6, which simplifies, but I'll just leave it like that for now, r squared dr dt. And we plug in the things we know. We know dv dt is -2. This is 15 pi over 6. We know that r is, we don't know what r is yet. We're going to have to figure that out. And dr dt is what we want. Right, that's the thing we want. So we don't know what r is, because they didn't tell us what r is, right? They told us a bunch of other stuff. They told us what is, we want to know this when the depth of the cherry raspberry mixture is 3. So they told us little h, and we know that, you know, we know this relationship. So we can figure out r, right? So if h is 3, and 5r equals 2 times 3, which 5r equals 6, r is going to be, right? So when h equals 3, r equals 6/5. So r is going to be, over here, 6/5, and everything's squared, right? 6/5 squared. And again, this is kind of like a messy thing, so why don't we just use a calculator on this, right? We know we're going to have to divide everything by this big number here. So what we're going to do is we're just going to do -2, and then we're going to divide by that whole thing, right? So it's going to be 30 in the denominator, right? So it's going to be, and it's going to be not 30 in the denominator, something bigger, but let's do it. Divided by, let's do another parentheses, 15 pi divided by 6, close parentheses, times 6/5 squared, close parentheses. There you go. That's -1.7. How many decimal places? 3. And you can truncate around. So it's -0.176. This is a radius, right? So it's inches per second. So like that's the non-exact answer, right? You can figure out the other one too just by solving this in an appropriate way. All right, B, how fast is the raspberry melt leaking onto Nino Corpi's school clothes? So you have to imagine it's leaking out of the cone onto his clothes, right? How fast is it leaking onto his clothes? Right, it's leaving the cone at 2 cubic inches, which means it's going onto his clothes at +2, right? If it's leaving at 2, then it's getting onto his clothes at 2, if that makes sense, right? because it's not like going to leave faster just because it's going on his clothes. It's getting on his clothes at the same rate it's leaving, but because it's going onto his clothes, it's a positive value instead of a negative value. So obviously he gets sick of getting on his clothes, so he goes and gets like a cylinder cup, a cylindrical cup. The cylindrical cup has a 2-inch diameter. How fast is the height changing, right? So now we have a cylinder, which we haven't done cylinders yet, but they're fun. Here's the volume of the cylinder. Volume equals pi r squared h. We know that dv dt, right? We found dv dt over here. We know it's going into the cylinder at 2 cubic inches. We want dh dt, and we know r. And this is the thing about cylinders that's nice. Think about if the diameter is 2, then r is 1, right? Half the diameter is the radius. Think about this. Does the radius change in a cylinder? Like as the mixture goes up, right? Is the radius changing? Like in a cone, it's obviously changing, right? Because as the mixture goes up, the radius is getting bigger and bigger, or as it goes down, the radius is getting smaller and smaller. But in a cylinder, like no matter where you are, your radius is the same. So the radius is a constant, which allows us to do this, right? I can just plug in a 1 before I do any calculus. And we get that. And then we can take the derivative of that, right? So I was allowed to plug in 1 now because it's constant. The radius is not changing. And we get pi dh dt. All we got to do is plug in our dv dt, which is 2, and solve for dh dt. It's going to be 2 over pi inches per second. Right, so cylinders are actually much nicer because the radius is constant, so you can treat it like a constant, right? The radius is not changing. And that's it. That's all of them. Hopefully this is helpful. I know it's long, but hopefully it's at least helpful.